Hello YouTubers. Thanks again for joining me for this series on how to use a multimeter for beginners. In this series, which will actually be the last part of this series for beginners, because after this we're going to switch to a series where we cover perhaps some more advanced features of multimeters and how to make some more advanced measurements. But in this series, part 3, we're going to look at continuity and resistance. And again, we'll have some analogies explaining those. But let's get stuck into the response to the question I had at the end of the last one, which is basically that initially when power transmission or power generation first started, DC was initially employed and then they switched to AC, and what the reasoning was behind that. And again, thanks to everyone who posted an answer. Again, it doesn't matter if your answer is way off. It's always good just to post an answer and then learn from what other people have posted themselves. Now I'm going to read probably 2 or 3 which I think are kind of most correct. I'll start off with Sam Gabriel. Basically in his response he was saying that it was a war of currents. In the USA in the 1880s, the key players included Edison, Westinghouse and Tesla, and then there was Steinmetz, which I didn't know about. So Edison was prominent proponent of DC, mostly for financial reasons, as he wanted his DC related patents to become ubiquitous and make him lots of money. Tesla advanced AC technology, and Westinghouse pushed the AC system in opposition to Edison. AC won in about 1891. So, as I recall from watching some history programs, I think there is obviously a lot of truth in that. But there was another key answer that I was looking for, and a user or a viewer called EEV Fan basically gave some maths about the losses, showing the losses that occur in DC current versus AC current. And I haven't actually gone and checked his maths, but basically he said if you're trying to pass, let's say it's something like 76 watts on AC, you'd be able to transmit about 80 amp DC, but on AC you can do about 390 continuously. And then probably the most correct answer was Kibi15, and he said it's easier to adjust the voltage of AC using transformers. You want high voltage for long distance transmissions to minimize power loss in the lines. However, you don't want those high voltages delivered to consumers. It's a lot more difficult and expensive even these days to adjust voltage levels of DC. And that is probably the most correct answer, because in effect that is your problem. You're going to have, as soon as you're trying to transmit electricity over long distances, you are going to have losses, particularly voltage drop. So you want to transmit at higher voltage. And I know in the DC, that when they're using DC, they basically had to have loads of kind of booster stations along the way to get that DC at the right levels to consumers. Now, as I said, DC, there's a problem with transmitting high voltage DC and then changing that voltage to a lower voltage. And if you transmit high current with DC, so you don't go too high voltage, you then need really fat conductors to transmit that electricity. Whereas with AC, you can transmit higher voltage far easier, keep the current low, so your wires are far smaller. And of course, as said, the transmission changing AC down to lower voltage and then obviously jacking up the current is far easier. So that was the right answer to that. Anyway, let's get stuck in and have a look at continuity testing and resistance. Okay, so let's have a look at some analogies to try and get a better understanding of what we're going to measure today with a multimeter, that being continuity and resistance. But again, first of all, I need to thank Comptest again for the loan of their Fluke 177 for this series. I think, as I said, it's a nice entry-level multimeter in the Fluke range, which I think would suit a lot of people if you are actually starting out doing electronics or electrical work. Right, so let's get stuck in and have a closer look at this, and hopefully I can get this across with some reasonable understanding in terms of what we're going to be measuring when we get to the multimeter. So continuity, if we go back to our hose pipe again and the tap which is pushing water through our hose pipe and the water is pouring out the end, continuity in essence just checks to see that we have a continuous path from one end of our conductor to another. Okay, so if we happen to chop this pipe over here and the water flow stopped coming out at this end over here, we'd have a problem, and we would want to try and find out where that break is. And that's in essence what we do with our continuity tester on a multimeter, is to check that we've got a flow of electricity, or if you like a flow of water, along a certain route or through a pipe between 2 points. Now this can be without, again I say we are going to have a more advanced series where we get a bit more down into electronics and how it all works, but on a circuit that can be quite tricky, and there's a few things you need to remember here, and these are points you need to remember when we start using the multimeter. For both continuity and resistance, you should have your circuit that you're testing de-energized, meaning you shouldn't have power applied to your circuit because it can be potentially dangerous. Unless you really know what you're doing or what have you, do not have your circuit energized. Right, so going back to continuity, if this was an electrical circuit, so pretend this is copper wire on a circuit board, and we've got some points here, we've got a break over here, and we've got some components over here, and we've got a break here, and we've got 2 exit points over here. If I had to take my multimeter and check continuity between these 2 points over here, and let me just label them. So you've got point A, B, and C. If I check between point A and B, have we got a continuous path? No, it's fairly straightforward. We can see we've got a break. So if this was a pipe, we would have water gushing out here. We wouldn't have water coming out at point B where we want it, and that would be a breaking continuity. And with our multimeter, if we put it over here and did the test, which I'm obviously going to demonstrate later, we would not get our beep. So then we'd have to start troubleshooting, and we'd take our multimeter and we could take it between another 2 points in the circuit over here and check, and yes, we'd have continuity over there, and we could take it between these 2 points over here and we'd realize no, we didn't, and that we could then start isolating and troubleshooting where our break in our circuit is. Now this can get quite complicated. If we were in an example now trying to check continuity between point A and C, we would have continuity, okay? But let's say we still had a break in our circuit over here, which was a problem for us. We needed flow across this component over here. Pretending there's a component over here and there's a component over here, our continuity test, in theory, if the resistance was right, would work. And if we put our leads over here, we'd get a signal coming back to us. And if we put our leads at this point down here and see, we would also have continuity because we would have a path through here. If we went down over here after this break and see, we would still have continuity because we'd have a path flowing straight up and over here. So in this case, in a circuit like this, you'd need to start removing components to help troubleshoot, because you can have multiple paths to the test point. And to troubleshoot that correctly, you'd have to start removing components to try and eliminate points points of continuity so you can find out where your break is. Now that's getting a little more advanced, but I just wanted to quickly highlight it that continuity testing can get quite tricky sometimes, and you have to be very wary that if you're doing it across an electronic or electrical circuit with multiple paths and components, you have to start pulling things out to start isolating where your continuity break could be. Right, so that's continuity. And I tell you what, before we get onto resistance, let's have a quick look at the multimeter and see how we can do a continuity check. Okay, so we've got our multimeter, it's switched off at the moment, and I said for this exercise we've got the Fluke 177. Most multimeters do have some sort of continuity tester, although some don't, and then you may have to resort to using the resistance test. But I tell you what, we'll cover that off when we get to resistance, how you can use the resistance test or measurement part of a multimeter to check continuity. In essence, it's the same thing, except the continuity tester has a nice buzzer to let you know when you do have continuity. Right, so our leads, again, the black one goes into your common connector, okay, and then your red one, you will have to look on your multimeter. It normally goes into the one with the voltage and the ohm symbol, okay, and that on this multimeter is that one over here. Then we turn our multimeter on and we flick it right round to this symbol over here, which is like kind of a sound, or almost like a sound coming out of a speaker, because that's where we test continuity. Now I want to highlight, I say, the one handy feature on a Fluke, which if you look at my multimeter reviews is something the Flukes are renowned for. And the one thing to do is always to check that your meter is working correctly. Hold your two leads together. Make sure you get a good response so that you don't start testing, and if your battery or something's wrong with your leads or your meter, that you suddenly don't get the results you want. But the Flukes generally have a latched continuity tester which is very quick and clear. And that, if you're a more serious user of a multimeter, can be very critical and useful, especially if you're checking small electronic components. So it's just something I want to highlight. Having a good continuity tester certainly adds a lot of value. Right, so we've got it there, and basically, as we can see, the reason we're getting that buzz, which means we're getting a complete flow from end to end between 2 points, is because we've got our test leads. It's sending a test current and voltage through the wire to the multimeter to see that it's got a continuous flow between this point and through the multimeter. And if we put them together, we get that beeping sound. So now when it comes to a circuit, as an example, I've got this switch here. Now again, it could be there are 101 devices and bits and pieces that you can test for continuity. It could simply be a piece of wire, and you don't know if there's a break in a piece of electrical cord, and you can, and I said, just remember what I said in the when I was showing you the analogy, always de-energize the circuits that you want to test continuity for. But if you've got that piece of electrical wire, you simply would place the probe at one end, the other probe at the other, and see whether you get a buzz or whether it's intermittent. Sometimes those can be the worst problems. You get something that works on and off. If you wriggle a wire around, you can then tell, especially if you've got a good continuity tester, whether you've got an intermittent fault or not. But here we've got a switch, and even on switches like this switch happens to be a double pole, double throw, if I remember correctly. So it's got several connection paths inside, but I might not know which one of these connection tabs on the switch are connected when it's on. So I'm actually just going to let me just put the multimeter down there. So the beauty is we don't need to look at the display for this example. We're waiting to hear the sound. So if I put my one probe over there to see if there's flow or a connection between these 2 points, nothing. If I put it there and over here, nothing. What I generally do when I'm doing this, because I always want to check that my multimeter is working and that my probes are working, I sometimes come back to where my initial probe is. I even touch, I might not directly touch the probe, but I touch the same piece of wire, the same piece of contact to make sure things are working. Right, so now I'm going to flick the switch. So when I flick the switch that way, one might logically think that these 2 points over here are connected. So I get my one probe tip and I get the other one, I put them there, nothing. I now take them to these two. Bingo. So when the switch is switched that way, I now know that these 2 points are electrically connected. Let's check the 2 far points. Not connected. These 2 not. These 2 are. So that's just a little example on how to test a switch and test continuity in a switch. But of course, testing continuity has got thousands of uses when trying to troubleshoot electrical problems, and it's one of the most common uses besides, let's say, measuring a voltage. Your continuity test is probably going to be one of the most used features on a multimeter for troubleshooting electrical or intermittent electrical connection problems. Okay, let's go back to the piece of paper and have a look at resistance. Okay. So now again we're back to either our hose pipe or our pipe which has got water flowing in it. And if you can imagine, if we have a normal pipe with water gushing out of it, okay, and you get your hand and you squeeze it tight in the middle, as I've represented here, either squeeze it or you've got a narrowing in the pipe, what's going to happen to the flow rate and the pressure of water coming out the other end? Both the pressure, so that pressure that would be flowing against you is going to drop and reduce, and so will the flow rate. Okay, and that means that basically, so when I talk about flow rate and volume, we're talking about both your current and in essence the amount of water which will come out here, and the voltage is going to drop. And that is in essence what resistance does on a piece of wire. Now again, it gets a little more complicated when you've got multiple pieces of wire and what have you, but that's what we're covering off here. We've got a single piece of wire or that single pipe with water flowing through it. You have a restriction. It's either squeezed, or if you can imagine here, I've got a piece of pipe and I've got a plate in the middle where I've only got a small hole in the cross section of that pipe. What's going to happen? If you suddenly had to slot that in, you're suddenly going to get a reduction in the pressure and the flow rate. And that in essence is what resistance is. And here is a resistor, and resistance in wire, basically the resistance is brought on by the cross-sectional area of a conductor or a material. So it could be copper, it could be steel, it could be silicon. The type of material will have an effect on resistance and its cross-sectional area. And as you can imagine, you know, the cross-section is like the size of your pipe, and then potentially the type of pipe that you've got will affect that flow. So you could have a pipe with very slippery sides in essence, which kind of represents like a material like copper or gold, which allows water to flow very easily. And you could have a pipe which, this analogy is perhaps not the most accurate, but let's say we have a pipe with fur or carpet inside it, okay, and it's a different kind of pipe. That may relate to a material like silicon or something like that, which doesn't allow electricity to flow as easily, or carbon for that matter. It doesn't allow electricity to flow as easily. So it's the cross-sectional area of material and the type of material. So what happens, so this is a resistor which we are going to measure right now, but without getting too in depth and going into Ohm's law on what happens with resistors in circuits. When you have that loss, a resistor, you've lost now some of your pressure and your flow rate, And if you remember back in science, things just don't get lost. Energy doesn't get lost, okay? It's dissipated. And what happens in a resistor of this sort, it dissipates those losses as heat. You'll get heat coming off your resistor. So let's move on to the multimeter and see how we measure that. Okay, so let's get down to how we actually measure resistance with a multimeter. So again, as we had before, our black one is in the common connector on the multimeter. Our red one is on that omega sign, or ohms, on the multimeter, which is normally shared with your voltage measurement. And then we just flick our selector through to the ohm, or that omega sign again. And the multimeter is set up to auto range, okay, and by default you'll see it sits here in this overload mode, because basically it's got nothing to measure. Now then, one interesting test and something to note is that even your multimeter leads can have resistance which can affect your reading, okay. So what you can do is put your probes together and just note, as you can see there's even 0.1 or 0.2 of an ohm resistance in these leads. Now, so there's a couple of things there. There's either potentially calibration on or accuracy of your multimeter, or that literally is the resistance in your leads. Now, if you're measuring something really critical, you might need to actually note that. And on some multimeters, you'll have a button that you can push, a relative button, to cancel that out. So to, in essence, zero or take a relative reading where it discounts that reading on the screen. But that's just something to note. Okay, so let's get to our switch. So if we have it in the up position like we did before, and we put our two probes between those 2 points, you can see we've got the overload on the screen there because it hasn't got any reading. There's no continuity between those 2 points. I should go to these two, because actually, depending on where the switch is, it could be either of those. And if I switch it this way, I think we'll note, yeah, there's no continuity there. We go here, and there we go. We've got that 0.2, 0.4 now. So remember, basically, as I said, there was that resistance potentially in the lead. So in essence, we've got close to zero resistance going through here. Okay, I say that, and as I play around, you can see we're getting just above 1 ohm. So this is also where you can check continuity if you don't have a continuity buzzer, is to put it to the resistance setting on your multimeter and check resistance. And you kind of want obviously as close to zero as possible to show that you've got good continuity. Right, so now let's get to the resistor. This is going to be difficult. I might have to use press stick, but so here we have our resistor. And what I'm going to do first is I'm going to take the tester. In fact, I'm going to get some press stick because that's going to be just a little bit challenging with that moving around. If I take a measurement on this side of that resistor, on that wire, we can see we've got basically almost 0 ohms. Now if I go to this other side, across the resistor, it is 1 kilo ohm, so 1.000 kilo ohm. So that is 1,000 ohms across that resistor. Now let's get another resistor. And again, you'll note this is out of circuit, because if you're trying to find resistance in a circuit, you're basically measuring the resistance between all the components between your two probes. So if you want to measure something specifically, sometimes you have to be very careful. You have to take it out of a circuit to actually get a good clean reading, or else you could have other components within a circuit which could upset your reading. But here we go. We put the two probes on either side of the resistor. I just have to push down to make sure we get a good clean, and there we go, 390.3 ohm. Now again, remember, so this is a 390 ohm resistor, but that 0.2, 0.3 at the end is that potentially the resistance which is sitting in your leads. So I say, if it's something really critical you're measuring, just remember you have to account for even the resistance in your leads itself. And literally, it's as straightforward as that. Just placing them on either side and picking up the reading. You can even measure the resistance of some interesting things like through my body. So there we go. I'm holding the test probes tightly in my hands, and there's about 1 mega ohm. Okay. And if you had to sit and do it on the same finger, now that's interesting, 2.3 mega ohm. I would have thought it would have been less the other way around. But you can do some quite interesting things. I'm just going to quickly lick my finger. Very gross. But here we go. We take a reading and look at that. Having moisture on my hand is changing the resistance. So the flow of electricity between those 2 points. So anyway, there we go. It's as simple as that. I hope you found this whole series useful and interesting. I will be starting up the next series, which is kind of the more advanced uses of a multimeter and advanced measurements, where we'll get into things like measuring current with current probes and shunt resistors, and measuring consumption, energy consumption, and all that kind of thing. So if you're keen to join for that, or think someone else might be, then certainly do share these videos or subscribe. And again, if you've gained any value, then please do give it the thumbs up. And in the next series, I'll find a new set of quiz questions so that we can post them and answer them, and hopefully they'll give us a better understanding of electricity and electricity measurement. Thanks very much for watching.